Yeah, I just. Okay, awesome. So today I'm going to be talking about data splitting, something that we call data poisoning, which is basically just a scary way to say that you didn't use super rigorous data practices, and so your results are not necessarily super valid. And then also a little bit about just benchmarking in general and the way that computer vision researchers think of structuring and using these benchmark data sets. Okay, generally in computer vision at a very high level, we're trying to estimate some version of this. This is classification. There's many different, more complicated versions of the output. But usually we're just trying to ask some question about what is in an image, right? And the way we think about that is we think about constructing a model, and usually that model is then estimating some sort of probability. So here you're saying we're estimating the probability of category Y conditional on the input X, given the class X. And so maybe this model gives you, okay, for us, that's 95% estimated probability of elephant, 5% giraffe. The important thing here is that for most of supervised models, supervised machine learning models, we learn to estimate this probability in a parametric way. We learn it from data. And so, generally, if we're trying to think about ways that we learn models from data, and I'm going to try to keep this really mostly conceptual. I'm not going to go into a lot of the underlying probability or the math, but just in a conceptual way. When we're thinking about learning models from data, let's consider this very, very simplest version, which is learning to categorize these points on a plane based on their color. So you have a bunch of points on the plane, some are blue, some are orange, and we're trying to learn some sort of model that will enable us to say which points are going to be blue and which points are going to be orange. So we assume that we have here some sort of representative data. And what we mean there is that we assume that all of these points are drawn IID from the same distribution. IID being independently and identically distributed. Just like a pretty general concept that means that your assumption is that the points that you are going to try to model are all coming from the same underlying distribution. And we also assume, in this case, that we have labels. So here, when we're trying to estimate, say, that probability of X given Y, X is going to be some, 2D coordinate NM, and Y is going to be blue or orange. So using our labeled data, say we learn this linear classifier. This is something where basically we can just say everything on one side of the line is blue, everything on the other side is orange. How do we know if that model works? How do we know if this is a good linear classifier? So, what we did here, essentially, you could assume, is you just said, okay, well, here's all our points. Here's blue, here's orange. Here's a line we can draw, easy. But so now the question is this model actually right? Now, it's definitely right if these are all the points you're ever going to consider. But usually what we're doing is we're actually using some data that we've sampled, some assumed examples of data, but that data isn't actually all the data that we'd want to be able to categorize. So one thing we could do is we could get more data and label it and then test our model on that new data. Usually that just isn't what we do because it's impractical. We already have this data, we've worked hard for it. And so usually what people actually do is they just pretend they don't have some of the data and pretend that that data is going to then be, the data that you'd evaluate that on later. And so since we're assuming our data is IID, then it's reasonable to randomly sample and say, okay, some of these points are training points, which now I've colored lighter. And then some of them are going to be points that we use to evaluate whether the model worked. And so here now we would learn, say that model using just the training data. So now this is some subset of the data that is that we're pretending is all the data that we have at a given point, and we're using that to try to understand what works. And then we'd say, okay, now let's look at those extra points that we've held out. Is this a good classifier? Did we get it right? And here, great, yay. It works perfectly. We have this beautiful model. It worked exactly on our validation data. But actually, there's a lot of different ways that we could draw that line, right? If you have these input points, there are many, many, many different possible, completely 100% correct classifiers on the training data. Then not all of them are right on that validation data. And so here, you probably would look at the results on this validation data, and you wouldn't pick one of the models that's wrong on the validation data. But this actually means that you're using the validation data to select your model, right? So if we decide what classifier is the best based on how it does on the validation data, that means we're using data for model selection. And so then if you're using data for model selection, then it's not actually unseen data. So this means if you want to maintain the integrity of your model evaluation, you need to then further subsample your data set to include a test set that you do not use for model selection. And I would like to point out that a ton of the papers you read in machine learning are terrible at this. They, especially some of the benchmark data sets we use, what we will see is the test labels are public. And so people will not use the validation and the test data as they actually should be, like in a sort of integrity-driven, rigorous way, be used. They will, because they're trying to get the best number on a benchmark, try running 1,000 different TPU hours worth of models and pick the best one based on its performance on the test data. So that combination of some data set, a task, and how to evaluate it. So, here the task is orange versus blue, and our evaluation is, did you do it with orange versus blue? But obviously evaluation can be much more complicated, and we're going to be talking about evaluation early next week and some of the complexities when it comes to your type of ecological tasks. And then this train, validation, test split, where you have something that you're using to fit the parameters or train your initial model, something that you're using to select the best possible model, and then ideally this test set that you only look at after you've chosen a model, and then you don't get to make any more changes. That is called a benchmark. And these benchmarks have played a really integral role in computer vision research. Computer vision, for a very long time, didn't work. There was basically decades of computer vision research where we would come up with some very, very complicated, very human-generated set of features that would look for edges and contours and curves and use that to determine whether you could detect, say, human faces in images. And then they would show an example where this complicated method detected human faces in images, a cherry-picked example, and that was the state of computer vision research for a very long time. And this push towards standardized tasks, standardized benchmarks that enabled the community to try different methods and compare them against each other in a really standard way was one of the things that actually pushed computer vision to the point where it started to work. And we started to be able to really try to understand how models were failing and how we could make them better. And I mean, the other big components here were data scale. So the ImageNet benchmark is one that probably even all of you have maybe heard of if you've talked about computer vision at all. It came out, it's close to a decade ago now, maybe a bit less. And it was 1 million images over 1,000 different categories. So it was the largest data set that had sort of been curated up to that point. The other important factor in terms of getting computer vision to work was GPUs. Was basically building computers that were able to do lots of multiplications in parallel very fast, so that you actually could scale up the size of the models that you're actually learning. And so these days, unlike a linear classifier, most computer vision models are some basically massively non-linear system of equations that takes in an RGB input and gives you some sort of structured, informative output. Beyond, ImageNet, one of the first benchmarks was MNIST. Jason talked about that in his talk, which is just like this standard way for people to try to understand what works in what doesn't. CFAR is another one that people will throw out. Those are very small images. Both MNIST and CFAR are now almost, they feel like toys compared to some of the larger benchmarks we now work with. COCO was the first big object detection benchmark. ImageNet was image classification. The list goes on. There are thousands of benchmarks in computer vision measuring different things. But it turns out designing benchmarks is super hard. And actually designing benchmarks that are representative and good benchmarks for machine learning based science, not just for like, is this pizza or is it a cat, but something that you're actually going to use for science, is very difficult. This was a workshop just last week at Princeton on the reproducibility crisis in machine learning based science. And they did a set of reviews of different fields and looked at the papers in those fields that were using machine learning and categorized which papers had pitfalls and what those pitfalls are. And you can see, for example, in medicine, there were 27 different papers that they found that just didn't have a trained test split. They just trained a model on their data and showed the results on the training data. Autism diagnostics, there were 3 different papers that had duplication across training and test. So their data wasn't actually completely separate. The list goes on. But one thing that I think is really, really informative for this community is 17 out of the 17 papers they reviewed in satellite imaging did not have independence between their train and test sets. So basically, they were taken, for example, at the exact same time and place. So this is super hard. And this is really what I want to get at is like with this lecture, I want us to think really critically about the data we're going to use, how we want to think about splitting the data, and then if we get results on this data, what claims can we make? What do we actually know about our larger problem? And this is one of the big ones. What if that initial assumption is wrong? What if the labeled data we started with wasn't representative of our problem, wasn't representative of the entire space of data that we might want the model to work on? So say we used our model and we trained on it, and then we want to use it on data, and it just turns out that data sampled from a larger value of M. It turns out our model was just dead wrong because we didn't have any data from those larger M values when we were training, validating, or testing the model. So we just didn't actually have any way to claim what's going on there. So here, the domain of the original data, that's the data that falls within that red circle. And the terminology that's often used is now that new data was out of domain. It was basically outside the scope of your benchmark. And so you can't make reasonable claims necessarily about data that's out of domain. And so, ideally, what you'd want to do is learn a classifier that works on all possible data. You want to basically know that you have something that will always be able to tell you whether a point's going to be orange or blue. But that's really hard if you've never seen data outside the red circle. This actually isn't an unfamiliar concept for all of you. In ecology, this type of challenge is called extrapolation, right? People know that if you build a species distribution model, for example, on one national park, and you tried to then use that species distribution model, even just at a different national park next door, usually it doesn't work. So we really, this is a statistical challenge, right? And it's something that is going to be an underlying challenge for almost any type of science. I think the insidious problem is that with computer vision and machine learning, we can get overconfident. And so, you know, I really want to point out that these types of domain shifts, basically like that the data that you want to use the model on might not be from the same domain. Those are really ubiquitous in real world scenarios. This is a paper that I was one of many amazing authors on, where we tried to formulate a benchmark that captured these real world domain shifts and measured actually how much of a problem, how much of a gap we got in performance when you ask a model to perform well out of domain. And one of the things that we looked at here was evaluation frameworks that can help you understand how bad you might do out of domain. Ways to think about building a benchmark that explicitly measures in domain. So here with camera traps, this is examples of data from those same cameras, but data that isn't seen during training versus out of domain. Examples from cameras that were never seen during training, entirely new locations. And we found that looking at macro F1, which is a metric that measures a combination between precision and recall in a class average way, we saw a 16% degradation in performance going from in-domain cameras to out of domain. And this type of drop-off in performance from domain shift is basically always true. You see this looking at histopathology in hospitals, shifts in time across satellite images, even for the same locations, shifts across regions, looking at wheat head detection, but wheat that's grown in different parts of the world, shifts in terms of bioassay prediction. These types of domain shifts are ubiquitous in the real world, and they're very hard for computation. And one thing that we found that was very interesting is often people will ask, well, how many images do I need? How many images do I need to get this to work? And it turns out that, so here what we're looking at is the blue line is in-domain error. The red line is out-of-domain error. This is on a data set, a benchmark that I created called Caltech camera traps. And then on the bottom axis, you're looking at the number of training examples. And we plotted each species and then put a best fit line through all the species. And so what you can see is that, yes, it is true. The more training examples you have, the better. You see that error go down consistently, and the error is in log scale. So that's like pretty significant. You know, few examples is hard no matter what. But also that domain shift problem doesn't go away if you have 1,000 examples. You know, it will continue to be there. You will continue to see performance drop off out of domain, even if you have very, very common species. So, you know, I think just to really hammer the point home, the real world is not IID. Try to imagine what data set you would need to capture the entire distribution of your problem in the world. The real trick is that, one, that species are changing. The ecology of the world is changing over time. It's changing faster than ever due to climate change. So if you could capture this perfect data set that had exact labels for the entire world today, one, species move and migrate and change over time based on environmental covariates, based on access to food, based on temperature change, but also there's this slow yearly change due to climate change. And so I think the important thing to realize is that trying to collect a data set that is going to be entirely in distribution is going to be an impossible task. Now, that doesn't mean that all hope is lost. It just means that we want to be very careful about what we're claiming. And we also want to be very, very careful about how we're evaluating models. And then we never want to stop doing quality control. You never want to build a model, put it out, and then just trust it and never look at the results. You basically always need to have some protocol in place where you're verifying your results and checking them over time and figuring out if you need to retrain your model to then shift that model domain back to what you're actually trying to look at. So why is this so hard though? Like what makes domain shifts so hard? So one thing is subpopulation shift. So here what we're talking about is, given the same set of possible species, there are different likelihoods of those different species depending on where you are on Earth. So if you learn a species classification model on data captured here in Southern California, you're going to learn that coyotes and deer are very common. And then if you take that model and you bring it to the northeastern United States, the deer will still be common, but the coyotes won't anymore. And you've implicitly learned a prior in your model that says that, honestly, if you see something that looks dog-like, maybe it's likely to be a coyote, but now what that's learned is no longer true. And then you also have this extension of that, which is that you have open set populations. So there are species in some regions that don't exist in others and vice versa. And so you'll have actually entirely new species that you might need to categorize if you're doing species categorization. There are extensions of this to basically any ecological problem. So, this is actually even more complicated. If we look at our camera traps, this is the class distribution for individual cameras in the same region. So because animals themselves are habitual, you can also see subpopulation shifts that happen just based on microhabitats and individual animal habits. So those shifts in the distribution across your class set, they're not even just representative necessarily of the overall species distribution. They might be even more specific. And then what we found is that this is looking at some results on a data set we published looking at urban forests. And if you look at the L1 distance between the normalized distribution over the class sets for each city, L1 distance is just like if you made that distribution a vector and you look at like the cosine similarity between the two vectors. And then you look at the accuracy of our model. If you train on one city, test on another, so in a pairwise way, you can see that there starts to come out a lot of structure. You can start to see that similarity in distribution using a vanilla off-the-shelf computer vision model is a strong predictor that your model might actually do okay. Or it's showing that there's similarity between the distribution, underlying distribution of species in a city and the performance of a model generalizing to that city. And the other way that domain shift is hard is visual shift. This can be a lot of different things. It can be different camera angles, different types of sensors. So if you're doing remote sensing, going from Landsat to Sentinel, different backgrounds, different individual animals, different ages of animals. Some animals have a ton of variation, and some trees or plants have a ton of variation between their youth stages and their adult stages. What these things look like at night versus day, what they look like in the summer versus winter, what they look like wet versus dry. This is one that we ran into quite a bit actually, is that we couldn't recognize the same individual snow leopards when they got wet. And so what we'll see is you'll have high visual similarity in data from, say, one camera trap. So you can totally see, now this is very in domain, predicting on one and then testing on the other, it's not that hard. Those are pretty clearly the same species. But even across camera traps in the same region, you can get a lot of visual difference. You also get temporal, seasonal changes in background and what the animals themselves look like. I just always show this because I think it's insane. This fire blew through past this camera trap, did not burn the camera trap, and then like just a few days later, the same coyote was back. And then this is looking at the neon crowns benchmark, which is one that Ben Weinstein put out. And you can see that different ecosystems then have both of those things. They have both this difference in subpopulation. Here it's like a difference in the density of trees, as well as this visual shift. These different species of trees, what these trees look like, are different in these different neon sites. So first little think, pair, share activity. You have 5 minutes for this. I want you to just look to your next door neighbor, and I want you to talk to them about what is your targeted use case? Like, if your model was perfect, what do you want it to do? And based on the data you're using at this school, what generalization issues are you going to encounter? Cool. All right. 5-minute timer, go.
Do you want to do is there any
targeted use case? I want to try one generalization.
maybe
And for all the possible it's very hard.
Yeah.
That's very, very much.
No reliability.
Yeah, so my
trying to have a model that's very
Yeah, as well. Yeah, I think also sensors, things like snow and ice. Let's see. What am I
Yeah.
Now your new data is.
And I realized that,
yeah, it's like, and you just get it accurate.
Yeah, I mean, definitely a lot.
There's a lot of
There's one
So they also want to use like different regions that you're training in.
About 1 more minute.
Only a farm. They want to use it for outside.
Yeah,
Okay, that's right.
The background.
Yeah.
I also have.
Yeah.
And a lot of them are just like.
Outside.
Bring it back, everyone. Awesome. Okay, I hope that was useful. And hopefully it'll kind of help you also as you think about these projects and going forward. So I wanted to talk about a couple other things that you might want to think about in terms of benchmarking. So one is sample efficiency. So we talked about how for a prototyping data set, when you're sort of getting your code together and sort of getting these preliminary results, you don't want your data set to be too big because you don't want it to take 4 or 5 days every time you train a model for you to even just vet that your code is working. So one thing that you want to think about, and this is just sort of one, sort of example here, is sample efficiency. So some ecological data, a lot of ecological data can be pretty repetitive. And it turns out that a lot of repetitive data during training doesn't actually help that sort of generalizability at all. So here, this is just an example where we sub-sampled camera trap data. We looked at first using 100% of the training data and looked at the out-of-distribution test accuracy. And then we sub-sampled that data by half and then by a quarter, just completely randomly. And you can see that the actual model performance really didn't change that much. So the sample efficiency of that data was quite low. And you know what? Might as well just take a random sample of a quarter of your data if your data is going to be really repetitive. So just food for thought when you're thinking about the ways that you want to sample. But then there's also other ways you can think about sampling, right? Because if you have a really imbalanced class set, you're not going to want to randomly sample, because then you're going to basically start subsampling the number of rare species that you have in your training data. And when you have something very rare, we saw that it's very hard. So you basically want everything you can. So there's different ways that you can handle highly imbalanced data. And some of these are based on training efficiency, but some of them are actually just based on what you want your model to learn. So if you have imbalanced data, you might want to balance your training set by subsampling those common classes. This means that now you're not actually getting to see all the examples of the common classes you have. But again, if they're very repetitive, that might be really not that informative in the end anyway. You can also balance your training data set by just upsampling the rare class frequency. And this is something you actually can do in your data loader. You can just say, like, we're going to show the model the rare classes more than we show it the common classes to try to like increase the amount that those rare classes are actually affecting what the model learns. You can also kind of do that in your loss function. You can just penalize the model more when it messes up on rare classes. And we'll go into that in more detail potentially later. That's what these class balance losses would be. But you also want to think about how you're going to measure the performance of imbalanced data and of a model on imbalanced data. And so one thing that people do a lot in computer vision is they'll build a balanced test set. So for example, the iNaturalist data set, the training set has this very long tail distribution, but the test set has 3 examples per class. Now it's 10,000 species that they're trying to categorize. So 3 examples per class is still 30,000 test examples. It's a lot of data, which is why they chose to do that, because it just started to be a bit insurmountable otherwise. But that means that now your test set, when you build evaluation metrics, what you're measuring is, if you just look at accuracy of a balanced test set, you're basically saying that a mistake on a rare class is exactly the same as a mistake on a common class. And that, I think there's value in that. But when you think about the practicality or the usability of a model, if you're making a mistake on common classes, and then you're going to see those common classes all the time, in terms of the volume of just overall accuracy, how often you can trust your model, that's going to have a much bigger effect on the usability of that model than making mistakes on rare classes. And this is where it all gets very complicated and is going to be very dependent on your specific use case. What are the risks for you if you miscategorize a rare species? And so what I usually like to do is try to maintain a test set that has a realistic distribution, because then it enables me to try to measure both the kind of usability of the model, like what is a user going to actually see, but also then you can also look at class balanced metrics that tell you, are you doing worse on rare species or common species? Yeah, go ahead.
By realistic test distributions, do you mean like the frequency that the images would actually occur, like in nature, or?
I mean, it depends on what you're trying to do. So for me, it's like if I'm looking at a camera trap problem, I will take entire held out camera traps and maybe like a month of data from that camera trap and say, okay, this is test, because now I'm basically evaluating what would this model do if I collected a month of data from a camera trap. Or remote sensing, it can be really interesting for so many negatives. And so one thing that I'll see that people do is they'll sort of build an artificially balanced test set that has, you know, balanced positives and negatives. But then if you're getting a lot of false positives, and then you have this huge swath of like what the entire Arctic, for example, and you get a lot of false positives, that rate of false positives, those are all going to need to be human verified. So it's going to take a lot of human time. So it's more just trying to think about how do we measure the practicality of a model and also like maybe the reliability of the model. And like I said, this is actually where your ecological domain expertise really comes to play, because you understand what you need the model to do. And so now it's like, how do you figure out how to construct a test set and a training set that will tell you, is the model doing what I need it to do from an ecological perspective? And that's what computer vision scientists can't do, because they don't understand your problem. They don't understand the risks of different mistakes. And so they are going to make a worse choice about evaluation than you would. Okay, so now you're gonna take another 5 minutes and you're going to go into that working document and you're just gonna sketch out your plan, and it could be the plan you came in with, or if you have any food for thought after this discussion, feel free to put thoughts in there. But just sketch out, this is the way I'm planning to split my data, train, val, test. And then basically the idea is that we can discuss these with instructors during the work time and start building them. If you already have it built, great. You can start working on describing it and documenting it. About 1 more minute. Okay, awesome. Cool. So you'll have plenty of time later to continue to flesh that out. And also, I think particularly this type of thing, it's important to note that there basically are no right answers. Like there's not like, oh, this is the right way to build a benchmark for your problem, because each of you have your own questions, your own data, your own whatever. So this is something that I would very much recommend you discuss with each other, you discuss with us. And also remember that these data sets that you brought to the school are for prototyping, but now as you go forward and you try to maybe expand your model, expand the data, you can think very carefully about what you want to add to try to be able to both train and evaluate in a broader way. And I think just like as a last thing, I wanted to point out that like this type of rigorous experimental practices, these careful choices of benchmarks, they do actually enable impact. Because if you build a model, if you build a model and you have a training and test set that are not, you have data poisoning between them, you say you have all the same camera traps and you train a model on some of that data and you test on some of that data, you get 99% accuracy. And you say, great, we have a 99% accuracy model, but it turns out you want to claim that that model will work for other projects or other people working on the same species, and then they try it and it's nowhere near 99%. One, they're gonna stop trusting you. And two, they just can't use it, so it's not impactful. And when I started working with Microsoft on camera traps, our goal was classification. We wanted to build image classification models that could do species level classification for camera traps. But we set up, we understood that we wanted it to work for anybody. We wanted it to work for new projects. We set up evaluation practices that had these splits that were looking at new regions, new cameras within the same region. And what we found is that while species classification is still super hard to get to generalize, and particularly for rare species, that we did see that these off-the-shelf models could detect animals in a generalizable way. And so then we basically put in all this effort to, publish and build infrastructure around this model, but we knew that it was going to be usable by others because we tested it that way. And this model, the mega detector, now gets used by 60 NGOs worldwide. We processed 100 million images last year. And it's a pretty integral part of the pipeline for camera trap data processing for basically every large organization that uses camera traps. And that's really cool, and that makes me so happy. And that wouldn't have been possible if we weren't trying to construct benchmarks that were representative of our use case. So just a very final think, pair, share. I want you guys to talk to your partners about if your results are really good, what can you claim? And if you want to be able to make a broader claim, what data do you need to use? What data do you need to collect or add to be able to make that claim at a larger scale? Go for it.
Actually, it kind of does well in Europe.
But how do you know whether something's? You have like good coverage.
So,
How well.
So like, but yeah, they were all.
Yeah, so I guess I would I wouldn't mind. But I almost like very
Kind of like,
but only if I have different years than currently I have doing training like the same years. So but you're able to say that I can predict it for every year. Only 2 years of data. I hope that I 1 year of training.
So, yeah.
That doesn't work very well. I think you don't have like a year.
Data provide the area with the same. I would definitely need.
Yeah, you're very quality. But also data I could say.
My second part is.
You already have some
It's more than now. It's like a whole system like it means that for different applications, it becomes easier because there are larger differences.
That might be an implementation that
Because for this task, it will be easier. More data,
Okay, everyone, coming back together just at the end, I'm just gonna I'll take maybe 1 or 2 questions, but then also you're welcome to bug me about this at any point. So anyone have like general questions, probably not questions about your specific problem.
So with the you mentioned that like the benchmarks were what actually revolutionized computer vision's performance. My question was, within those data sets, are they pre-split? So like, is everyone testing on the exact same images or validating on the exact same images and training on the exact same images? Is that the whole point?
Yeah, the whole point is and this is actually a good thing for you guys to know. If you want a computer vision researcher, if you want to try and bring the computer vision community in and get them to work on your problems, you have to hand them something to do where they don't have to understand the domain. So it's like, if you build a benchmark that's very representative of your actual problem, and you tell them, you get to train on this, and you get to validate on this, and this is the test data, and this is how and this metric is how we're gonna measure your performance. That is what a benchmark is. And yes, every single one, ImageNet has training data and test data, right? And validation data. And then depending, sometimes data sets like benchmarks won't explicitly have validation data, and they'll ask, like the users are sort of allowed to validate on their own data. This whole issue with people overfitting on test sets means that a lot of Kaggle competitions, for example, they actually have some random set of the test data that they don't show on the leaderboard while people are competing, and then the final leaderboard is calculated on that unseen test data because people will overfit. And often, I mean, I've had casual competitions I've run where the top 3 all swap around, like when you go to the invisible test data, right? And so then the person who thought they won didn't win. Yeah.
I have a question about like the concept of test data in general. So for example, in well, I guess like in like competitions and you get like, you know, your like winners, if you're selecting, you know, the best model based on those winners, then don't you need to like test them one more time or something? And then, and the same like, just like, and how I think this is like relevant to me, like imagine that I had my train test, validation test like split, I publish a paper and I'm like, oh, I now have an idea on how I could make this better, and I use the same train validation test data. And then, isn't that cheating too? Like, how do you really make it like test data?
Yeah, it's super hard. And remember how I said, even in our field where we know that we have to do this, we're bad at it. People constantly peak essentially at their test data. And yeah, you're right. You publish a paper and then you go to publish the next paper, but now you know what your model did wrong before and you're trying to correct it. So I have actually been trying to think a lot in my own research about like, how do we actually try to think about evaluating these models in the real world in a way that isn't a fixed benchmark data set, and particularly thinking about the way the world is changing over time. If we curate a data set and we keep working on it, but things have now changed, if the model works better on that year of data, for example, we don't know if it's actually better today. And so I've been trying to think a lot about ways that we can try to do like kind of more online verification, or even like human-driven or community-driven verification, where say there's a model for remote sensing and you want it to be able to work for your country or for your specific area. How do we build systems where you can efficiently like go in, be asked to label some of that data and get results now completely for a new thing. But like, you know, where the data that you're going to use to evaluate actually sort of has this human in the loop component. And so you're like looking at verifying in an expanding way using the community.
So the test data is not a fixed thing, it changes.
Well, so now, you know, you as the community, so you as like an ecologist get to define what the test data is for you. And that can change over time, right? But this is like pretty non-standard. And it's definitely, once you move into a space where you're evaluating the model differently for different people or different use cases or whatever, then it becomes much more complicated to try to say model A is better than model B, right? Some ways, like what we're doing now with Wildlife Insights, for example, which is like this, you know, 47 million camera trap images over 40 countries, and we're trying to build species classification models that work for everyone. This is very hard. And we actually have generic evaluation, but then we break down evaluation by taxa and we break down evaluation by region. And what we often find is that we'll add a bunch of training data. The model will get better, but it doesn't get better for everybody. And so then it's like, you know, if you're actually trying to build something that's at that scale, how do you really build a model that's optimal for every user and their use case, but still sharing information when it makes sense, as opposed to having 1,000 models that are each trained on a smaller data set that might, you know, still do worse, like open areas of research. But you're totally right that being very honest and clean with test data is super hard. And I think one way that you could think about doing it is like, if you write a new paper, keep that same benchmark so you can compare, but then like add new test data. So now it's like, okay, now here's like a new one and we look at this, and this is what we saw here.
Cool, thanks.
Yeah. One more question?
Are there any like protocols or like really good papers that handle visual shift that would be informative for like how to incorporate that within the training sets? Like, you know, like, is it like having different variables for like wet, dry, different seasons, you know, things like that? Like, how do we make sure that we're incorporating that variation?
Yeah. I can try to see if I can pull up some papers. But I think remember when Jason in the very, his first lecture, he was saying, it's so important that you understand your data. This is kind of what we're getting at, right? It's like part of, and that homework 0, where you're like just plotting the distribution over time, over space, over night and day, like just different ways to poke and probe at your own data to try to understand what you have. And then use your expert knowledge of the problem to try to understand what you might need to add, right? And it's an iterative process. I don't think in a real world scenario, in a setting where you want to be using these models in a practical way, I don't think I've ever seen something where someone built a benchmark data set, trained a model, tested it, and we're like, great. I feel like usually it's more that you start to understand that the entire process is iterative. You build a model, you get results, you rethink what data you might need to train on, you make changes, you add things in, you retrain, you get results again, you maybe realize now you have a new use case, you add more test data, and it just becomes this entire crazy morphy modular system. But I think breaking down evaluation in many different ways, and even thinking about for yourself, like just having some sort of eval script where like you just print out not just, okay, accuracy is blah, but you actually just generate like a big page that has all of these different breakdowns of performance and is comparing models across a bunch of different dimensions, just probing that performance of the model. That's really helpful. And the first 2 lectures next week are going to be all about different ways to do that, trying to like poke at your model and figure out what it is doing well and what it isn't doing well.
So is it more of a case of being aware of these shifts than actually incorporating them directly, like at the beginning, like actually including them as like labels, for example, that are incorporated? Or
this is really interesting. I've tried different stuff like this. Like we tried, for example, training nighttime models and daytime models, and then like comparing them versus something trained on night and day. We've tried giving the like metadata about the time of day. It turns out that I think because these computer vision models have so much capacity, they end up learning all of that implicitly.
okay.
And so it doesn't I haven't found that it changes the performance drastically to explicitly give it that information, because in the pixels, it can tell it's nighttime.
Right.
So it'll just learn sort of implicitly somewhere within that, like night versus day will kind of just get their own pathways through the model.
Okay.
Now, of course, it's not as interpretable, but I haven't seen that be massively useful. What is a very useful thing, and Bjorn's gonna be talking about this, is data augmentation that is sort of informed by these things. So if you know you need your model to work at night, you have less, and you see looking at your training data that your data is imbalanced against nighttime, you can look at, okay, maybe if we like convert images to grayscale and like darken the contrast as like additional data augmentation, that might help us do better at night. So you can like create data augmentation that helps try to cover the variabilities.
Okay. Thank you.
Yeah. One more.
This lecture made me think a lot about like what actually the model is learning. So for example, like a picture of an elephant like this, like let's say that I have a model that it works great every time I get my elephant, but then it turns out it wasn't really like looking at the elephant, but rather than like the other parameters of the picture. Has there been much success of like to try to make it the model more generalizable to like, background subtract everything, just have like only elephants, and then if I put an elephant, not in the savannah but in the jungle, it will do better then?
Yeah, this is also interesting, which is basically this question of like useful versus spurious correlations. So, I mean, we could have a whole conversation about this, but basically, even if you test on completely held out things, in practice, sometimes these correlations your model learns about the sort of interaction between species and their habitats, for example, in this case, can be useful. And so if you do background subtraction and you take the segmented out animal and they're just predicting that, sometimes you do worse than if you have that context. And when I actually talk to experts about this, like specifically I go birding with a bunch of like really good birders, and I'm a terrible birder. And I'm always like, how do you know what species it is? And maybe with an elephant, honestly, we have really good elephant classifiers. Elephants are not a hard thing, right? I mean, it's very specific looking. But for things that are more fine-grained, that are more nuanced and more difficult, if you ask an expert how they know what species is that species, they will tell you, oh, it's because they're on that tree, or it's because the way that they're moving and hopping on the ground is like iconic. So there's all of this other sort of contextual information that goes into that identification, that if you take that away, then why would you expect your model to be able to do it well?
Right, because a human wouldn't even.
But then you can also get these spurious correlations. So we have this image in one of our papers that we parade around a lot, which is basically like a machine learning model completely sucking at recognizing a cow on the beach.
That's funny.
And in that case, basically, the models learned that cow, the concept of cow, is a combination of cow and pasture, and it's not able to recognize them on the beach. And there are so many examples of this. This is when we were talking about probing your model and trying to understand what it's learned. There's so many examples of this in the literature. So like one very famous one is like the military was trying to learn to recognize like US jets versus like jets, Middle Eastern jets, like the make and model of them. And they were like, we train a computer vision model and it's perfect. And it turned out the model learned desert versus grass. And this is something we're also going to talk about next week in the evaluation. There's ways that you can try to probe your model, and there's an entire field of computer vision that's around like model explainability or model interpretability that tries to give more information about what the model's learned. But one very common thing you can do is you can actually just look at like the activations through the model and like of the different filters and like look at, given a model that has the right type of spatial structure, you can look at where in the image the model is paying attention to when it's making a decision. And that's ways we've caught some of these issues, right? If you're seeing that the model is looking all around the animal, usually a good sign that maybe it's not really learned the concept of that animal. But cropped box classification for camera traps generalizes better than whole image classification. And part of that is just because the background is no longer like the same background over and over again. You're at least getting some concept of variable backgrounds with the animals. But it's not just background, it's also pose and orientation. So like we do much worse at cameras that are placed higher because the angle that you're looking at the animal is a little different. And it's definitely sort of a little further out of like that sort of general distribution of average camera traps. So stuff like that. I mean, if you start probing the performance of your model along these dimensions, you can capture like, oh, turns out we're bad at this. And then at least you can tell people, right? Because your model doesn't have to be perfect and do everything. It can be super useful if it doesn't do everything. But you just want to make sure that you're communicating what you expect it to do well and what you know it doesn't do well. Okay, awesome. Let's go to lunch.